Hello and welcome to week 3 of Unleash Your Inner Game Dev. I'm Jamie Bentley and I'll be running you through today's lecture. Today we're dealing with prefabs, profiling and optimizing. In their simplest forms, prefabs is building your game with reusable parts. Profiling is what you do when you...
Hold on, Jamie.
Yeah,
Sorry, I don't think you've started the broadcast.
it says it started.
Okay, I'm sorry. I'm very sorry. Go on.
That's all right. Profiling is what you do when you need to optimize your game to make sure it runs at a better frame rate. You'll notice a lot with mobile devices you don't quite have the processing power that you do on PC, and we'll be looking at how to identify ways that your game can be optimized. And then after we've done that, we're going to look into making those optimizations as well. So we briefly touched on prefabs last week where we put them together for the platform game. And there's a couple of different ways to use prefabs, and there's quite a few benefits to using them within Unity, but pretty much the basis of them is you can use them as a base and then you can use them anywhere in your game. And they can be instantiated at runtime, or they can be already in the scene, and they can be edited independently of the scene. So if you're making a change to level 6 and you have an enemy in there, and that enemy is in level 1, 2, 3, 4, 5, and 6, you only need to make that change once, and it will then propagate throughout all the other scenes. So some classic examples of prefabs are like characters, and they can be used across screens, multiples at a time, etc. Enemies, scenery, weapons, user interface, basically anything can be prefabbed. You know, special effects, etc. Even cameras can be, instantiated at runtime. So first thing we're going to do is actually put together a prefab, very similar to what we did last week, and we'll just jump back into Unity over here. So over here, I'll just get rid of the existing one I've done. So here we have an enemy, which he's a very simple enemy. He just chases the player. He doesn't do all that much, and it's already pre-set up in the project that's been provided for this week. And very simply, it already has the enemy component on it, which is just this. So very simply, all this does is, on the fixed update, which is in step with physics, is it finds the player, it then looks at the player, and then effectively it chases the player, and this is where I just clamp the maximum velocity. So this is already done for you. So what we're going to do is we're going to make sure that is a prefab, and we're going to drag it into the resources. So that's now a prefab that we can use wherever. Now the reason I've used resources is you can load things from the resources folder dynamically. Whereas if I put it in somewhere else, for example, into art, I can no longer access that through code. I need to load it from resources. So what we're going to do is we're going to spawn this enemy in code. So this enemy that we see here on the screen, which I'll just bring up, we don't need him, so we can delete that. So the way I'm doing that is with this logic script. And this is all pre-done for you in the this week's project files. So very simply, I spawn between two positions, which are spawn A and spawn B, and then I spawn it a couple of times. In order to profile it, we have to spawn a lot of enemies to see any real performance impact. So here what you can see right here, and I'll just highlight it for those who are right here. This right here is loading it directly from disk. I'm not dragging it into an inspector window. I'm loading it via its name. And that's coming directly from resources, hence resources.load enemy. Now I've cast that as a transform, which you can see over here on the right side, because that's the type that I've called it. You can actually reload it as anything. It could be a texture, it could be a sound file, but regardless of how you instantiate it, you will need to cast it on the right side there. So while I've done that, you could also change it to player, and you would have a whole armada of players, which would be absolute chaos, but it is doable. So the reason you might load something dynamically, for example, in a game, as opposed to having it all preloaded, is you might come across a random enemy, and then once you come across the enemy, you need to load this specific set of rules or conditions or the effects that go with a fight scene for it. For example, Pokemon. When you go into a fight scene with the various Pokemon, you need to load the specific fight effects for it. And you would do that with something very akin to this. So that's a good way to do it. So what we can see here is, so just pop back into game view, make it a bit larger. So we have a lot of enemies floating about. And they're all fairly simple. They all just chase the player. There's no death conditions because this is for profiling. You're totally welcome to add death conditions. And this control system I've got will work on mobile. You just tap something on the screen and the pointer goes towards it. And then it can also hit the edge. So as you can see, these guys are quite content just to chase. And that's all done through their code. So any change I now make to this enemy right here will now be propagated regardless of where it goes. So if I set the speed to the maximum speed to 5, this is going to be fairly hard for people watching on the web demo to see. But you'll start seeing them all fly back towards me in a moment at slightly greater speeds than before. And it's kind of chaotic, but you get the idea. So I'll just bring that back down to 1. So that, in effect, is how we dynamically load a prefab from disk via code. Now, to break that into something a bit simpler, this is the only line that's actually relevant. Everything else is just because I'm doing it multiple times. This is the position for it, and it just finds, the position between those 2 points to spawn them. And this will be part of some optimization that we do later. Right now, I'm not even using that, which also means I'm not using that. So that was a quick recap on prefabs that we handled last week, but now instead of just dragging and dropping them into the inspector, we spawn them through code. And that's simply resources.load. It's well documented in the Unity manual, and I recommend you have a look at it. And just before we move on to the next section, I am going to ask Margie for some questions.
So we've just got one question from John. John would like to know, what is the difference between Vector 2 and Vector 3? Could you please give us like a brief overview of Vector 3?
Yes, I can. The easiest way to describe it would be a Vector 2. Let me just find some empty space. So a Vector 2 is Vector 2, we'll call it. A Vector 2 has an X, hang on, test, just so you can see the autocomplete. A Vector 2 has an X coordinate and a Y. So for 2D games, you'd use a Vector 2, so you'd have your X position and a Y position. So effectively, 2 vectors is just 2 floating points. A Vector 3 simply has 3 of them. That's the only difference. Instead of X and Y, it also has an X, Y, and Z. And there is also a Vector 4, which has a W. So it's all same. And that's pretty much the main difference there.
Yep. That.
Okay, that was the end of the question?
It.
Okay.
Yep. Oh, hang on, sorry. John asks, are there any guidelines around the number and complexity of enemies that you could use? Should it be considered by platform, and does it depend on the complexity of prefab?
Okay, well, yes, and yes is the short answer. It is very much platform dependent. It is definitely dependent on the complexity of the prefab and what it does in particular. So we basically try break any performance into 3 categories. You've got your scripting performance, which is your logic, like you can see on screen here. You've got your physics, which is its interaction with the world if it's using PhysX. And then you've got the art overhead. How many polys, how many triangles, how many textures, how complex are the shaders, are they pixel shaders, how many lights are going to affect it. So you need to minimize as much as you can without compromising quality. So in answer to the question of, is there a guideline? Well, not really. Test as quickly as you can. So when you start doing your prototypes or your white boxing, which is usually the first part of the game to make sure the idea is even viable, that's when you throw as much at it as you can to see what will break your device. So it's always good to work. For example, I've got a couple of Galaxy Notes here and some iPhone 4s, 4Ss, 5S. you should always try dev on the lowest possible device you have when you get to optimizing, and then that way you know all the devices in front of it, or newer devices I should say, are going to perform even better. A big mistake you can make is to pick up, an 8-core phone, be like, oh, this plays amazing. Then someone who's only got, say, an S3 or an S4, the game is a total slideshow and downright unplayable. So always look for the cheapest, most horrible device you're willing to support, and prototype as quickly as you can to know what your limits are going to be before you get there. All right, so I'm going to move on to profiling. Now, profiling is, well, pretty much just finding out where you are losing all of your frames per second to. And ultimately, with the exception of loading time for heavy art assets, the biggest issue with gameplay is going to be stuttering frame rates. This can occur because you're being sloppy with allocations, or you're too heavy on art, or you're doing too much math, or you're trying to load things dynamically, which I showed earlier. Yeah, any of these things can cause you some problems. So profiling is basically broken down into the profiler. So I'll just actually bring up the real one because it's a little more interesting to look at, which is right here. I'll just break that free. So this is effectively the profiler. Whoops, sorry. And I'll just start off with, by default, it records everything you do, but it only has a certain length of memory from left to right. There's also a deep profile toggle, which allows you to break it down into individual parts of each component that could be causing you some problems. This is very handy, and I highly recommend it. If you're on a very slow workstation, that will actually slow down your editor performance fairly substantially, but the data it gives you back is still very worthwhile. Now, another thing which we'll also show is that you can see an active profiler drop down. Once you build to device, you can change it, and you can set it to the device that you just built to, and then you can profile it on the device. The reason you want to test on device as much as possible is because this is a fairly beefy GPU multi-screen rig. It's designed to run really good games. It's not that indicative of what's going to happen on a mobile device. So what might take 2 milliseconds here might take a phone 20. It's not unrealistic to expect your PC to be 20 times faster. That might change in a couple of years, as it tends to do, but right now, PCs are far, far faster. However, bottlenecks are bottlenecks. You'll still be able to see where the performance hits are. So I'm just going to dock this window so we can see the game taking place. Just in this little window, I am sorry, but it will do. So when I hit play and the game starts, you'll see my profiler is doing all sorts of crazy things down there. And we'll just let it go for a little bit. All right, so you can see here that we've got little bumps and little... This is fairly common with anything that runs on the physics step. There's time between the physics, because if I'm rendering it, let's say I'm running at 120 frames a second, but the physics is only updated every 30 frames a second, which is what it should be set to at the moment, there'll be gaps between them. This is totally normal, but what you ideally want for a game that has a high frame rate or has a constant source of action, or has constant movement, is you want the flattest you can get, because it means that you're not getting big spikes. So up here you can see we are getting some spikes, and we can break those down. So on the left side of the profiler, you can see all these little, they don't look like tick boxes, but they are. So we're going to break that down. We're going to turn off global illumination, turn off others, turn off vsync. We're going to turn off the garbage collector. Now there's physics, which you see actually do make somewhat of a dent. And then there's rendering, which we're not that interested in because it's a fairly simple game. We just want scripts, and this is just what's coming out from the actual 3 scripts that I have running, which is logic, player, and enemy. So that's sitting there. And now if we scrub through, on the right is the very last frame that you rendered, and all the way to the left is, I think, approximately 10 seconds behind where you are in the game. So if we have a look here and break it down, it will say enemy fixed update. And if we expand that, we'll see that the most expensive thing happening is our transform lookout. It's using 12.6% of the total of this particular entry. So of the 42.8% that is attributed to the enemy, 12% of that is being affected with the lookout. We'll turn that off and we'll have a look at the difference it makes in the spike and the time. So there's a few major things to consider here. Now, some things do take quite a bit of processing time. There's nothing you can do about it most of the time. Some things just have to be done. And that will add to the amount of time it takes to process, which as you can see over here in the time drop down, which I've organized by the way, is 3.48 milliseconds. Another really expensive thing to do is when it allocates garbage. And that's on the left side. And that can be done when you do huge runtime allocations or you delete things and then C# has to go clean it up. On mobile devices, that can be quite expensive, but most of this doesn't really do anything that drastic. So you'll notice it's quite solid, sitting on 0 all the way through. So we'll have a look at a couple more things that might be causing, well, firstly, we can see that the lookout is the most expensive. Now we'll have a look at the corresponding script. So inside fixed update, which is referenced here, you'll see transform lookout. Well, there it is. So we know that that is quite expensive and it's costing us 0.93 milliseconds per profile a tick. That's not too obscene, but yeah, there are 50 of them. As you can see, it's been called 125 times per tick. That will be because there's approximately 100 enemies. I'd have to have a quick look, but there's roughly 100 enemies and they're all doing the same thing. There's also get component down here, which is doing its own thing. That's a well-known problem for Unity games. Excuse me. And you can see that we're also adding with some rigid body force. And there's also this game object.find, which is, where are we? This little guy here, game object.find. And game object.find is using 0.13 milliseconds per frame. So we're going to have a very quick look at some very basic code optimizations, which we're going to drop into this. Now, the general basis for all coding to optimize everything is just do less. The less you can do, the better. Easier said than done, but everything above the point where I say do less is effectively saying just that. Pre-allocate as much as you can. Don't do runtime resources.load if you can avoid it. If you can't, you have to do it. But if you can, please do. Only destroy objects when you're sure you're finished with something, which comes back to object pooling. Sometimes you'll have a weapon that fires very quickly. You might fire 50 shots a second. When that bullet ends, you don't need to destroy it. You can just turn it off and then use it again once you fire another shot. And that's called object pooling. Run less update loops. Consider using single control object. So update loops do have a very, very small overhead. And if you have 100 objects on mobile, you might start to see some issues with doing that, especially if they have fairly complicated pieces of code in there. You don't necessarily need to. You could run a single update loop on one parent object that does the same thing in arrays and iterates through them very quickly. And you might see some performance improvements from that. Use the power of coroutines to simplify update loops. Update loops are on all the time. If your game object is on, the update loop is running. You don't have to do it that way. You can trigger a coroutine that runs while the object meets some conditions. For example, you might have an AI script that looks around and looks for enemies while it's running. But once it stops running, you can disable that coroutine. You no longer have that constant overhead of looking for something or running a method. Cache components. Now, a component that we're doing here is this transform. I'm looking at the transform, but I'm looking for it every time we do a physics step. So we can cache that, and that's what we're about to do. Don't use send message or broadcast message. There's no reason. It just means you've poorly designed your project. A good example here is if my player hits an enemy, I don't then just send a message blindly that goes do something and hope that that script has that method in there. That's just sloppy. You should avoid doing that. If you hit it, you know what it is because it will have the appropriate tag or an appropriate name or maybe a control component that then tells it what it is, or it'll be a superclass of something. So always use a single get component is approximately 25 times faster than a single send message. So it's a no-brainer for optimizations. So the first thing we're going to do is we're going to look at the effect of this GameObject.find, which is causing us 0.013 milliseconds, give or take, per tick, which would be around here somewhere. So in this fixed update loop, we're doing that every frame. We don't need to do that. We can just put a transform here that says player. And now we do the exact same thing. We move it into start, remove it from here. That's it. So instead of searching via a string name every single frame, we now do it once. So if I save that, jump back into Unity, wait for it to unpause. There you go. So just fly around here, and we'll just pause. So we can still see the enemy is causing quite a bit, and we've noticed that the 2.8 or 2.9 that it was has dropped to 2.5. Notice there is no GameObject.find in this list. It's gone. So we've just saved ourselves, I think it was 0.3 milliseconds. Now remember on mobile that's 1.3 milliseconds. It does sound relatively trivial, but just imagine timesing it by 10 for mobile. So if you only have 1,000 milliseconds per frame, which I'll just bring up a calculator for you, 1,000 milliseconds, that means there's only 16.6 milliseconds per frame before you drop underneath 60 frames a second, which is ideal. Some games that are a bit slower, you can get away with double that, but it adds up very quickly, so keep that in mind. So that's the first optimization we're going to do. That's actually a very solid one at that. Now, the other thing we'll do here is just that's showing you a very minute or a more subtle optimization. Now we're going to do an optimization just to show the gross difference in this view, where if we remove the lookout. Now, the lookout goes up and down per frame, but it is effectively 4.4%, and it's giving us a fairly decent overhead. So if we simply remove that, and this does mean that the enemy won't know where to go, it's just going to fly around randomly because it's needed. So the enemy's just going to do its thing now because it's no longer looking at the player. But now you'll see that the enemy has actually moved down beneath the physics step. Instead of using the 13% of the total scripting, it's now only using 2%. So it's now much less of an issue than it was before. This would be considered an unrealistic optimization because it breaks game functionality. Typically, if you break the game, it's not an optimization worth doing. So that's that handled. Okay, so the next thing we're going to do, actually I'll just drop back the slides. Okay, so that's a very quick example of some code optimization. There's plenty more listed in the Unity documentation, which is in the notes at the end of this lecture as further reading material for next week. That's all the programming side. There is a whole other side to Unity, which is, of course, art. Everything in Unity, they've done a really good job of rendering natively to whatever platform they're on, be it OpenGL or Direct3D or Sony GL, etc. So textures are compressed. Now, this is a little harder to, in fact, it's basically impossible to benchmark on a PC running the GPU I have. But this texture I have running in the background here, and you can only just kind of see it there if I actually select it from this grid, which we'll go find. It's an art background grid. You'll see over here, whoops, sorry, that this is a 2048 by 1048 RGB compressed texture. It's being stored as 1.3 meg. So it's going to be sort of hard to see on this, this webinar format. But Let's set it to true color. Word apply. It's now 8 meg. That is a huge amount if you're pushing that much data per frame. Now, modern GPUs are absolutely amazing, but that is a lot for something that... Did you notice a difference when I switched it? If I set it to compressed, there is no visible difference. If you want to see the difference, we'll drop it down to 32 pixels wide. Now you can see it's become a blurry mess. I've overdone it. And it is 360 bytes though, so that's a good saving. So typically the easiest way to do this is to lower the art in quality as far as you can until you can't tell the difference, or until you can start to tell the difference. So at 2048, it still looked excellent. We'll drop it to 1024, still pretty good. Drop it to 512, starting to get a bit soft. So we'd call this a 1024. And now it's only 341K instead of what it was previously, which was 1.3 meg. So we've knocked out an entire meg of data, or megabyte I should say. Now we can save even more. We know that we're never going to see this texture on an angle because it's a top-down game. So I can go to advanced, and we'll just resize this window. And we can disable mipmaps. Mipmaps are effectively what you'll see in the distance or when it's smaller. It's like a cheaper version of the texture lowered, size down, so the GPU doesn't need to call as many pixels when it's rendering. You can turn it off, and you save 30%. And we're down to 256K for no visible difference from what was originally an 8 meg texture. So we've effectively saved 7.75 megabytes, thereabouts, just for this. Now, on a game this simple, that might not seem like that big a deal, but if you imagine a game the size of Zelda or a Bethesda game, that's huge. That could be hundreds upon hundreds of megabytes of file. So that's another optimization. Another optimization again is, of course, not having any lights. The scene doesn't have any lights. Lights are expensive every time you do them. You add your draw calls. Using cheaper textures. This one is using the mobile additive shader, whereas if you use the regular additive shader, it's a bit more expensive, and it's a pixel shader. And that means rather than just rendering using a very old format of rendering, it renders per pixel, which is substantially slower when you get to lighting. So that's also covered lights. Now, overdraw. Overdraw I haven't really mentioned much, but effectively, overdraw is when the GPU has to render the same pixel more than once. That's called overdraw. So you'll see this game, it's basically black. It does have a particle system playing behind it, which is not terribly elaborate, but it is there. You might be able to see that in the web software. Let's have a look. Yeah, it's there. And that plays behind, gives these little glows, which you may see in the preview. I can turn them up, but... Now, overdraw is effectively when you have the GPU has to render this screen, and then I'll just turn off the actual material on this one to give you a better idea. Should be 1 second. I'll do that a different way. Duplicate the grid, move it up in space, move it across, well, move it up, grab this texture, set it to none. No, don't open Photoshop. Sorry, my bad. My grid is popping up elsewhere. It's popping up on my other monitor. So I set that to none. I also set it to a different additive so I can make it a bit more obvious. Okay, so overdraw is when every single pixel is rendered again. So this is rendering once. It's doing that first layer of the gray grid. And now it would be rendering every pixel again. And then if I add another one on top of that, you'll start seeing that we've now got 3 layers of gray. So this texture up the top, this little gray section up, just the top gray section effectively, it now has to do a depth clear of every frame, and then it renders black over the top, then it renders layer 1, then it renders layer 2, then it renders layer 3. There's no enemies yet, and we're effectively rendering the entire top half of that scene 4 times. You want to avoid that. Do as little of that as possible. If you can get away with drawing everything just once, do that. So less layering of things. Some of it's unavoidable. A character on top of a background, that's just going to happen. But especially when you're dealing with additive particles and things of that nature, it can get out of control very quickly, especially with particles. Particles are very, very easy to, I guess you could say, exploit. For example, how do we show that? So you probably can't see it too well on the web software, but that's in wireframe view. And you can see that we are overdrawing a lot. So particle effects are something you definitely need to optimize sooner rather than later, because they can add up to be very expensive in-game. All right, so usually when you're prototyping your game, when you start prototyping, you benchmark everything you can just to get a general idea. You might not start optimizing, but you will see how many characters you can fit on the screen before it falls over. You might not have final art, but you might have a decent polygon budget. So when you're doing your early prototyping, see what breaks the device. Throw as many enemies in, throw lights in, just see what you can get in there before it becomes unplayable. Then bring it back to playable, as playable as you can. And from that, remembering that there's no optimization yet, set your budgets, your triangle budgets, your texture budgets, which shaders you can use, which you can't. The game might not look good, but it will still have a good performance overhead estimation of what your final game will have. Now you might think, but I'm going to optimize it, it will get faster. Yes, but you're also going to finish the game and a lot more stuff will be thrown in. Often you'll end up sort of balancing in the middle. Okay, so we didn't touch on object pooling, which I will do in just a minute. So I'm just going to quickly take some questions before we start doing some object pooling, which is another form of optimization.
Hi Jamie, do you or have you personally used a service for device testing, or do you just test on the lowest device that you have?
That's a interesting question. I have worked with dedicated teams who would work, test through the night in a different country, and then they would send back their feedback in the morning. I've worked at studios where we just have 30 devices and we all just get builds and test. When I'm doing, if you're just doing contract work for someone, you'll just aim for the slowest device you have. For Android, you need a couple because things might not work. Android especially has some issues where what works on one might just crash another, specifically OpenGL3 support and the Samsung S3. Very problematic. So you can do it, basically you work within your budget. If your budget is to have 10 people who test full time, awesome. If you don't have that, test with the worst device you can possibly get. And the other benefit of that is they're usually quite cheap. And just see how you go. If you can get it playable on a terrible device, it means everyone with good devices is going to have a good time.
So how can you access from a script two of the same kind components within an object, i.e. penguin, i.e. the penguin had two circle colliders? So how can they access each circle collider independently from the logic?
That's a good question. You can do what's called a get components in children, and it will return you an array. Let me just grab a web browser to bring it up. Okay. Anyway, it's it's called get components in children, and it will return however many of that component type there are. Now they'll usually have a name, and they'll be in the same order that they were added. It's also good sometimes to make a customized version that doesn't work that way, or with the way I did that penguin. I did that for the sake of brevity. You should probably have your separate collider as a separate object, as a subchar, because rigid body takes all children colliders into account, and that just makes things a lot cleaner. That actually answered that question. Yep.
Last question. Oh, sorry, I lost the... What other tricks have you used to reduce the memory hit or disk access when, for example, reduced graphics may not be an option? Are prefabs, graphics, or game logic more memory hungry? And do the tricks always stand up under different conditions, such as networked games?
Yeah, that's that's a long question. All right, so breaking that down into its smallest pieces, code has the lowest memory overhead. Textures and audio have the highest overhead. Mesh, not so much, unless you're importing architectural visualizations, which are millions and millions of polys. So I'm just trying to think of the best way. Yeah, so for networking, you don't send any of those things over the network. The client already has them. That makes things quite easy. You just have to account for the fact that the client might not be ready. So most things like Photon, etc., they have a buffer and they can store the messages for when they become relevant. Or if you're trying to do things a little bit more custom, you need to take into account that the other client may not have loaded the asset yet. Now, as to lowering the hit on loading in stuff dynamically, which if you have an endless runner and then you change worlds or things of that nature, you do need to load things in on the fly. You can either load them in tiny pieces, or you can load them in asynchronously, which is relatively new to Unity. It can be a little stuttery still, but it does load things on a separate thread, and then when it's done, it will return true, and then you can use that asset. As to the actual overall memory consumption, just do less, less textures, less sound. You just have to cut until you make it work. That should answer that question.
That seems to be it.
All right, so next we're going to fire on to object pooling. And I'm going to show you the effect of not object pooling first. And we're going to do that by loading up the logic where I spawn all of these guys. Void spawn enemies. So this entire spawn script now occurs inside spawn enemies. I'll just make an I enumerator. We'll just say spawn enemies. Bam. Oh, I shouldn't have called that the same thing. Spawn timer. Okay. So now what we're going to do is we're going to spawn some enemies like that, and then we're going to yield return you wait 4 seconds. We're going to wait 3 seconds and then do it again, and then we're going to do that again. So now we need to go start coroutine, and we're going to do that with, don't worry about the usage of the coroutine. It's not required for the homework. I'm just doing it for the sake of showing a profile of spike that would be unwanted when you're playing. So now when we start, let's just make sure the profile is running. Bring this up here. All right. So the game starts. 1, 2, 3. 50 enemies spawn. 1, 2, 3. 50 enemies spawn. Notice the spike. It gets bigger and bigger and bigger every time. Now that's effectively because we're spawning more enemies. Well, we're never going to need that many enemies on screen, you'd hope, unless you're doing geometry wars, in which case you do things very differently. But you will see that there is an overhead, and finding the exact spike can be slightly difficult. I'm just going to find it. It could be any one of these. One of these, you will see the actual spike of the spawn. All right, well, that's taking too long. I assure you there will be a spike from just suddenly throwing 50 enemies out. So if you aren't going to have more than 50 on screen, but you do always want to have 50 on screen, rather than destroying them when you complete them, or when they die, you can just reuse the ones that are off, which is what I was talking about earlier, which is object pooling. So move up to here, and we'll just we'll keep that on because that was kind of cool. Just spawn enemies, delete that. Now remember I said earlier that we had these enemies here that we weren't using. We're now going to use them. So when we spawn the enemies, we spawn that many. And then enemy index 0. So then what we want to do is we want to store it. The enemy we just spawned, that is, equals new enemy. Hi. Oh, sorry, just new enemy. Just get component enemy. So now that we've done that, you'll notice that my actual index here is wrong because I'm doing it through I, but I'm doing it in a nested loop because I do j number of i's. So we don't want to do that, which is how come I did this here. Enemy index plus plus. So every time we do that, it will use that integer and then it will also increment it in line. So we'll just hit play and we'll wait for it to compile, hit play, and we can see that there's only one enemy for some reason because I've broken something. Enemy prefab, enemies, there's none there. I'll just restore this back to how it was. I'm not entirely sure why that only spawned one, because the enemy index should be untouched. Let me just do that and make sure. Still working. Ah, here we go. It's not set to a... Yeah, okay, so basically it's telling me that the enemy that I have spawned does not actually have the enemy component. Now, I can probably guess that that is incorrect or that I've made a mistake purely by the fact that by dragging the enemy prefab itself, we can see here that it does have an enemy script on it. So what I need to do is see where I've gone wrong with that. Maybe change out the game object or component and see if that has repaired it. The reason that's not working is because it's thrown a null. And the enemy component is not being shown as being true. Okay, I'm not entirely sure why that's not working. Let me just force this to use the 0 index. And then if this, let's just quickly double check to make sure that component does exist. Enemy component exists on the prefab. Back to there, do this, plus debug.log. So we're also getting a very crash course in sort of rough debugging here. I'll just move that over to here, and I'm missing semicolon. So the reason this isn't working is because it's saying that new enemy doesn't exist. If new enemy equals null, debug.log, there is no enemy. Let's double check to make sure that's true. Correct. So for whatever reason, this enemy that I'm creating is not existing long enough to work immediately under it. So let's just do this. I can't honestly tell you why that isn't working, so I'm going to do it a different way. We're going to have each object register itself instead. Ordinarily, I would have done it the other way. It isn't working, so I'm going to have to think on my feet here a bit, but that's okay. So, register enemy. Enemy, new enemy. So now we've still got our enemies defined because they're defined here. Enemies, enemy index plus plus. Oops, sorry, and I'll just need to put that in here. I've done that wrong. Close that, equals new enemy. So that's all done. Now what we do is when the enemy exists, we're going to have it find the logic. like so. And this is also an important part when you have inter-object communication, which we haven't really touched on so much. But when you need to communicate with other objects, first you need to find them, and then you can access those components. Find the game logic, and then send it some information. So we know that we're an enemy, and we know that the game logic has a script called register enemy, and we're just going to send it this. Now this is just a global call to this component. Whatever this is the component that is executing the script itself. So now when we play it, we can see it's all working, and if we go to logic, we can see all the enemies are actually in existence. Sort of had to MacGyver that code on the spot. This registering enemies is something you would do specifically a lot of in multiplayer games, not so much in single player games where you know what you need to spawn ahead of schedule. For multiplayer games, for example, you might suddenly end up with 20 players you weren't anticipating, so you need to register them somewhere so that you have a link to them. Otherwise, the only way you can interact with them is to start searching for them through the hierarchy via code, and it can be very messy. So you don't necessarily want to do that. So what we're going to do now is when excuse me, when the player hits a character, or an enemy, sorry, we're going to disable it. So you might recall last week I drag and dropped some on collision code. This is, well, this line is from the manual, but the rest is all custom. So what we're going to do now is when this rigid body, which the player has on it, hits a collider, which are all the enemies, it's just going to turn it off. Relatively simple stuff. So we hit play. All right, now it's going to be hard to see via the webinar software, but this little guy, if he's left to his own devices for long enough, will eventually turn them all off. Probably shouldn't have added so many because they're kind of hard to see, but there's less of them now. All right, so we'll pause it. You'll see down here that a lot of these objects are now off. Now, when you're doing object pool, if you're not doing object pooling, the first thing you would do is you wouldn't just disable it, you would just destroy it. Now, occasionally you do need to destroy things, so I will show you how to do it that way. And you would simply just go destroy, and that's it. It will have the same visible effect in terms of gameplay, but it will remove the object from existence. So if I hit play, you'll see my my bar on the left side is getting smaller and smaller as I remove the enemies just by crashing into them. It's not, you know, an amazing game, but you will see that I'm getting less and less of these enemies because they're being destroyed. Now that can be useful, but we want to reuse them. We always want 50 on screen. So we're going to do that. Turn that off. So that just disables them again. Now back in logic, we're going to once again add our enumerator. Whoops, enumerator. And we're going to call it respawn. Yep. So once we spawn the enemies, we then want to start this coroutine. Respawn. Now this is a fairly simplified code. Obviously, if you're doing a proper larger game, this is all going to be wrapped in a lot more logic than this. But so the while true simply means that this is going to keep occurring forever. Yield, wait for, sorry. Yield, return new, wait for seconds. And we'll just do this every 3 seconds. So every 3 seconds, put that there. We're going to find an object that's on, and we're going to do that with for I equals 0. I is smaller than enemies.length I plus plus. Now this is just what's called a for loop, and it's going to iterate through every single enemy, which, let me just hit play for a second. So here's all of our enemies. Effectively what we're going to do, because logic now has a link to them all on the right side, you'll see here. And every time I click them, you can see where it corresponds on the other side. I'm going to look for one that's off. If enemies my.gameObject.active, and we want that to be false. Enemies my.gameObject.setActive true. Now, at the moment, this is going to do it for all dead enemies every frame, or sorry, every 3 seconds. But if you're doing something like bullets, you might not want it to do it that fast. You might want to just turn them one at a time. So we'll see these, let's just try kill some, just whack them. So you'll see they're off. That one is off, and then suddenly he's turned on. So effectively, they will now never end, regardless of how often they hit me. They will just keep reusing the same enemy stash. Now, in a proper, larger, more detailed game, you're not just going to turn them back on. You're going to respawn them in a new position, which we could effortlessly do just with a, we'll just put them in the center for the sake of ease. But position equals vector3.0. Where's that? Did I miss a close bracket? I did too. Sorry, my mistake. So now when I hit play, you'll see them respawn at the center. Now they're all bumping off each other because they're spawning right on top of each other, which, depending on how old you are, is called telefragging, spawn killing. There's all sorts of different names for it, but effectively they're all spawning in the center. So we'll just quickly jump back to Profiler, and I will show you another method of optimization which hasn't been touched on. Now, for Geometry Wars is a good example because it's fairly similar in style to this. Some enemies could interact with each other, some could not. I'm just going to very quickly show you how to optimize your physics. So this is your control, or I should say your collider lattice would be a good term for it, but it's a collision matrix effectively. And you can set which colliders can collide with what. So if we say that the player can't collide with enemy, and then we hit play, well, nothing's going to happen. No one's going to die because that collision has not been called. As far as physics is concerned, these items will never touch. We don't want that. What we want is the enemy can't crash into the enemy. So when they spawn in the center, after you've killed a few of them, they're just going to deal with it. And they'll just spawn in the center. You notice they didn't pop out vertically like they were last time. And I can also see that they're spawning with quite a bit of speed. So we'll just quickly change that for the sake of showing it. And we're about to do you probably wouldn't do this typically, but it's where you go get a specific rigid body on a particular object inside a logic. You try to keep everything self-contained. You should probably add a stop moving component or a stop moving method to the enemy script rather than doing it like this, but this will just quickly show you what happens. Hit play. So I just whack a couple. When they spawn in the center, you'll see they're all spawned in a big clump because they can't collide and they're all now set to 0 speed. So if we just quickly fly around, set this back to shaded. So you see these super bright ones. They're super bright because there's several all on top of each other. So effectively that's object pooling. Object pooling is when you have, let us say, 50 objects, be them projectiles, enemies, or whatever, you reuse them rather than deleting them. That's a fairly quick implementation of it, but it works well for particles, bullet impacts, bullets, rockets, explosions, even blades of grass, especially blades of grass, I should say. And you've got these little tree clusters, etc., and bushes. You'll end up reusing these objects over and over and over. You don't need to load them in dynamically if you can just reuse them. And especially for mobile gaming, where clearing out your memory is quite expensive, because for every object you add and then you delete, that memory doesn't necessarily just get reused instantly. Sometimes all the existing script backend behind it, etc., will create garbage. When Unity clears that garbage, there is a huge spike in performance. And this is covered in the Unity documentation, which is just coming up. So that concludes week 3, where we covered prefabs, profiling, and optimizing, specifically with object pooling. And the homework for this week is you'll be able to take this project and optimize it. Now, I only touched on a couple. The additional optimizations you're going to find in the Unity manual, because it is a great resource and it's going to mention quite a few things that you can easily do to the code that's there. The code that is there is purposely, inefficient. I'm doing a string search per frame, per object, things of that nature. There's some other optimizations you can possibly do, and I'd love to see some profiler comparisons up on the forums. So I think I will take one last round of questions if there are any.
Yep. So, what practices would you recommend to decrease health risks associated with game development? For example, how do companies reduce back injuries occurring in employees over time, etc.?
Okay, that's more of an occupational health and safety question. However,
Yep.
Some studios will offer you gym membership. I mean, I work in front of a computer, not even exaggerating, probably 16 hours a day. I'm slowly developing a hunch. So go to gym, work out as much as you can, get out of your desk as much as you can. That's basically the best you're going to be able to do, and eat healthily. It's a very odd question to have in the middle of an optimization lecture, but it's the best I've got.
Would it be more efficient to add the dead enemies to an array so that you don't have to search through all of them?
Yes, it is quite common to add a list or to have a dictionary that you just continually add to. The only concern is sometimes it can be more expensive if you have, say, 200, 300 objects, removing things from that list and resizing the list can be a little expensive in itself. The way I do it is not necessarily the most, what would be the appropriate term? It's not the prettiest, but it is fast. It is the absolute fastest way you're going to be able to do that. Normally I wouldn't search through an array. For something like an enemy, I would use a list. For something like bullets, where I know they're going to fire at an iterative rate, because I know that a bullet is going to live so long, and I could just iterate through the list, 1, 2, 3, 4, 5, 6, 7, 8, 9. This method is best. This method I've used here is not great for enemies where they could die at a random rate. You are correct. You should use a list, and there's actually quite a few plugins that are dedicated to object pooling, and that's how they do it also.
When would you be using real modeled bullets instead of ray casting?
Bullets would be used in, say, shoot 'em up, R-Type, Xenon 2, Mega Blast, Project X, Assault Squadron, which is one I worked on. That if you're thinking of first-person shooters, you're limited to rockets and grenades, but if you start thinking arcade games, try thinking of a game where you didn't see the bullet. It's just a slightly different way to think of it.
Is it important to remove useless objects for game optimization?
It depends on the style of game. If it's like a platformer that has a set start, has a set end, you know the level's going to end, it's not really that important. If you have a game where, like an endless runner platformer or just something procedural that just keeps on going, then definitely you should remove things if you're sure you're not going to reuse them.
Mm-hmm. And there's just another two more. Does Unity manage threads well, or is it up to the programmer?
If by threading you mean a different CPU core, Unity doesn't. It does some of its own internal tools, like the skinning of meshes, etc., physics to some degree, particle systems. They're all moved off to a separate core, but the scripting by default is all on a single thread. You have to then go do that yourself. And the mono behavior that you use for the basis of the majority of scripts, not all, but a lot, it doesn't really respond well to threading. So this is a whole different sort of subject in itself. I could easily throw a couple of lectures at, but what you want to do when you need to start using those other cores for computative, tasks, is you want to bring that into core C#. You want to have all your own classes. You don't want to rely on anything that inherits from mono behavior, so that you can just reliably know that you're getting data back from the threads in proper sync in time, things of that nature. But by default, just trying to move some characters or change some transforms in one thread and then change them, a couple of others in another thread, not a thing. Don't try it.
So Chris would like to know about using backed light maps for optimization.
Baked light
instead of baked.
Yeah.
Oh, sorry, baked lighting maps instead of GI and baked textures, etc.
Yeah. I personally am a huge fan of doing the baking myself using my own 3D Max pipeline or 3D Max Photoshop. It's a bit of a hybrid. Definitely. I highly recommend doing it, especially for mobile, because the default global illumination system is not, I mean, it's good, but you don't have that much control over it, and your artists will eventually start bashing their head against the wall the more they play with it. It's not a good look. So if you can, definitely do it yourself. I'll just quickly show you the texture from just a project I'm working on, where the background is entirely pre-baked. This is a project of mine, which hopefully will work. So I've, well, I didn't do this, an art director I work with did, but everything is pre-baked, the lighting, the shadows, the glows, etc. So when I render this in the game, there's nothing to take into account. It just magically works. It's as fast as it possibly can be. So yes, bake, bake, bake as much as you can. Keep as little as possible rendered with proper lights. And if you do that, you'll be able to get, the difference would be if you dynamically light a scene, you're using every pixel on that screen to render lighting. Why not pre-bake it? It looks possibly better than doing it dynamically, and you'll be able to fill it with characters or objects or trees or whatever floats your boat.
Awesome. So I'm not sure if you've answered this. Is the optimization from baked light mapping significant?
Yes. If you mean from going from the Unity one to the your own one, I think it's still faster. I haven't got my own solid benchmarks of that, but you will notice that every time you make a change in your scene, Unity needs to rebake. It does get a little intrusive, even though it is a background task. And if you hit play or you build, it will then go fix its light maps. Whereas if you have a solid pipeline where your artist is his own individual thing, he knows what he's doing, he will iteratively go update it, and you just won't need to think about it. It will just change in your scene. When he updates it, that's it. It's a one-off, it's pre-baked, it's handled outside of Unity. And typically, to be perfectly honest, you have more control in your 3D package, be it Blender, 3D Max, XSI, Maya, whatever, than you will ever get using the Enlighten system in Unity.
Awesome. Last question. Is it viable to use Unity for a graphic novel style game?
If by graphic novel you mean like Max Payne or...
I guess something, yeah, or like Phoenix Wright, like where it's like a visual novel with like
text and things of that nature. Yeah, you can. To be honest, I've been using Unity for 6 years, 7 years, a long time now, and there's not much you can't do with it. It's just sometimes you might not think of how to do it until you get there. I mean, I've built apps with it, like actual apps, not games, and it did the task just fine. And the other benefit of using a game engine to make apps with is you get very good looking apps. You get cool effects when you touch things, and so yeah, Unity is extremely versatile. You definitely could do a graphic novel style game or a book reader if you really wanted to. I know that's not quite what he asked, but I'm just saying it has that range. The only thing to consider when you do build to mobile is that an empty Unity project is 10 meg, or 10 megabytes, I should say. It has an overhead just to get the initial engine there, but if your entire app is under 100 meg, it's not a big deal anyway. So yes, you definitely can, and I'd like to see someone try it.
Awesome.
All right.
But yes, thank you very much for answering all these questions.
No worries. All right, well, that concludes week 3, and I look forward to seeing all of your stuff on the forums, and I will see you next week.